Okay, let's dive right in. We're going to explore one of the deepest, weirdest, and most misunderstood debates in the entire history of physics. It's a story about a scientific giant who thought he found a crack in reality itself.
So picture this. It's 1935. The most famous scientist in the world, Albert Einstein, thinks he's found a huge flaw in the hot new theory of quantum mechanics, a flaw that seemed to violate the most sacred rule he had ever established.
Back then, a lot of his peers kind of wrote him off. They thought he was an old man, past his prime, just unable to get his head around this radical new reality. But his objection wasn't just him being stubborn. It was a deep, logical worry that would kick off a scientific mystery lasting for decades.
To really get why Einstein was so bothered by all this, we first have to go back and appreciate his greatest achievement, the idea of a universal speed limit. See, before Einstein, people like Newton thought gravity just acted instantly. Like if the sun were to just, poof, disappear, Newton believed we'd feel it on Earth right away. But Einstein showed that this action at a distance leads to all sorts of paradoxes where effects could happen before their causes. So he set a new rule. Nothing, not even gravity, can travel faster than light. All effects have to be local, rippling through spacetime.
But when Einstein looked at quantum mechanics, he saw a major problem with something they called wave function collapse. The idea is that before you measure a particle, it doesn't really have a definite position. It's more like a cloud of possibilities. The moment you look at it, that cloud of maybes instantly collapses to a single definite point.
And that's the word that drove Einstein crazy. Instantly. He argued that if you make a measurement here, the particle's wave function collapses everywhere else at that exact same moment, no matter how spread out it is. And that was exactly the kind of spooky action at a distance his theory of relativity was supposed to have gotten rid of.
So of course this set up a massive clash of titans. It was Einstein versus Niels Bohr, who was pretty much the main architect of quantum theory at the time.
Now, to really nail down his point, Einstein and his buddies came up with this amazing thought experiment, the EPR paradox. Here's the gist. You create two particles that are linked. They're entangled. If one spins up, you know the other has to spin down. Now, you separate them by a whole galaxy, and you measure particle A. You instantly know the state of particle B. The question is, how did particle B know what to do?
Einstein, well, he proposed a much more sensible idea. He said there must be some hidden variables, like secret instructions that each particle carries with it from the very start. That way, no faster-than-light message is needed. Bohr's side? They basically said, hey, don't even ask what's happening when you're not looking. That's not a question for physics. Just do the math, predict the measurement, and be happy.
For decades, pretty much the entire physics community sided with Bohr. Einstein's really deep objection was mostly pushed aside, treated like a quirky philosophical footnote.
And here's the reason why. If you actually ran the EPR experiment, both quantum mechanics and Einstein's hidden variables theory predicted the exact same results. And if you can't test it, well, it's not really physics, is it? It's just philosophy. Or at least, that's what everyone thought.
The whole vibe in physics became shut up and calculate. I mean, the theory worked incredibly well, so why poke at its foundations? The mystery just went cold. And then Einstein died in 1955, with his deepest worries about the nature of reality still unresolved. But then, decades later, in 1964, a physicist named John Bell dusts off this old, almost forgotten paper by Einstein, and he takes it seriously. He wasn't happy to just leave it as a philosophical argument. He figured out an absolutely brilliant way to finally settle it with a real experiment. Bell added this crucial little twist to the EPR experiment. He asked, what if the people doing the measuring on each side could randomly choose to measure along one of three different directions? It sounds like a small change, but it turned out to be the key to everything.
Okay, now this is where it gets amazing. Bell proved that with this little twist, the two theories suddenly gave different testable predictions. He showed that if Einstein was right, if the universe was local and had these hidden instructions, then the measurements would disagree at least a third of the time, 33.3%. But spooky quantum mechanics predicted they'd be more in sync, disagreeing only 25% of the time. This wasn't philosophy anymore. This was a number you could go out and measure. It was the smoking gun.
So all that was left to do was actually build the experiment, run it, and ask nature itself which set of rules it plays by. And when the results started coming in, they were crystal clear. Time and time again, the experiments found a disagreement rate right around 25%. Nature sided with the spooky, non-local predictions of quantum mechanics.
So here's the thing you really gotta get. Einstein was right. He was right to be spooked.
He correctly saw that quantum mechanics had this weird, non-local connection baked into it. He was just wrong about what that meant. Bell's experiment proved that any theory that correctly describes our universe has to be non-local. Spookiness is just a feature of reality.
But wait a minute. If these spooky connections are real, does that mean we can break causality? Can we, send messages into the past and create all sorts of time travel messes?
Thankfully, the answer is no. And here's why. Quantum mechanics has this built-in safety lock. Even though the correlation between the particles is instantaneous, the actual result of any single measurement is completely fundamentally random. You can't force one particle to be spin up to send up one dear friend, so you can't actually use this to send a coherent message. The universe is spooky, but it's not broken.
But what if there's one last, wild, completely bonkers way out of this whole spooky mess? An escape hatch to try and save Einstein's dream of a purely local universe.
The whole spooky problem, right? It all comes from this idea of the wave function collapsing when you take a measurement. So, what if we just get rid of the collapse? What if it never happens at all?
Well, this leads to the absolutely mind-bending many worlds interpretation. It says that when you measure a particle, the universe itself splits in two. Instead of one outcome being chosen, both outcomes happen, just in separate parallel realities. A version of you sees spin up, and in a brand new universe that just branched off, another version of you sees spin down.
And this, right here, is the incredible choice we're left with. Do you accept a universe with real, faster-than-light, spooky connections? Or do you accept a universe that is constantly branching into an infinite number of parallel copies of yourself just to avoid it? The big takeaway here is that no matter which one you lean towards, the fundamental nature of our reality is far stranger, more mysterious, and more wonderful than any of us ever imagined.